Thought platform, and I welcome to all of you, and we will going to start our today's talk. So for this I will invite Mr. Ashish Pandey to come and introduce our speaker. Mr. Ashish Pandey. Ashish Pandey.
Thank you, Daniel, for inviting me. Today we have invited very eminent Dr. Lakshmikant Mishra. He has done his PhD from University of Allahabad, and currently he is giving his services in Bhavans Mehta Mahavidyalaya, Bharwadi. So, without wasting any time, I would like to invite Lakshmikant sir to uh, to start his talk. So, Lakshmikant sir, hello.
Okay, thank you, Ashish. Am I audible?
Thank you, sir.
Ashish, am I audible?
Yes, sir. You are audible.
Okay. So, thank you very much for your kind introduction. And I thank Ashish and Gyanendra and other persons from Mathematical Thoughts to inviting me to give a talk here. Okay. So, let us start. Topic of my talk is an introduction to some non-trivial groups. Okay, so I wish to present my screen. Wait a minute.
Sir, you have joined with mobile or laptop?
Laptop.
Okay, sir. So you can go in right corner. You see audio cut and video. So there is three dot in the right corner.
Okay, I'm doing
Okay.
that one. So it is. Wait a minute, just.
Yes, sir. Your screen is visible now.
Okay. Well, groups. Okay.
Yes, sir.
So let us start. As you know very well, what is the group? Okay, so group is what? Group is a non-empty set with a binary operation O. From O is what? O is a function from G cross G to G. Okay, it is called binary operation, which and you know very well that if it is binary operation, then suppose we take 1 minute. Actually, I am not used to very much, so there may be some problems. So forgive me for that. Suppose we operate O on A comma B. So what we get? A, O, B, and this is another member of G. This is also called closure property. Okay, so set G with binary operation O is called or is said to be a group if it is associative and it has identity element, and if for every element there is inverse. Okay, you know very well that it is an abelian group if operation O is commutative. Now let's come to some examples. So we are talking about some trivial groups. Okay, so we are familiar with several trivial groups, and first one is what? First one is set of integers. Okay, set of integers. This is very much trivial group. You know very well. And this is an infinite abelian group. Okay. In fact, it is cyclic group. You know what is cyclic group? Cyclic group is a group which has single element. Okay. So this is trivial group, and there are some more trivial groups like R with operation plus Q. Q means set of rational number with operation plus, set of complex number with operation plus. These are other trivial groups. Okay, so these are with operation addition. Okay, so suppose we wish to take some examples with operation multiplication, then we have R plus. R plus means a set of all positive real numbers. This is also a group with multiplication. Okay, and set of positive rational numbers with operation multiplication. This is also an abelian, infinite abelian group. Okay, and we cannot talk about a set of positive complex numbers since there is nothing positive or negative. Okay, so we have some non-zero complex numbers C star with operation plus. Sorry, not operation plus, but operation multiplication here. Okay, so this is another trivial group, and similarly we can talk about some other non-zero set of real number, set of non-zero real number with operation multiplication, and set of non-zero rational numbers with operation multiplication. Okay, so these are some trivial groups, and we are talking about since it is trivial, why it is trivial. So since we know very well these groups. Okay, so we wish to think about some finite groups. So what are some finite groups? So trivialist finite group is what? This is Zn. Okay, what is Zn? This is a group of residue classes modulo n, where n is a natural number. Okay, so this is okay. So this is a group with operation plus, where how the addition operation is defined here. So if we have two elements R bar and S bar, so we add these two elements such that R plus S whole bar. Okay, so you know, I think you will be knowing it, that if we take some simplest example, suppose Z5, and we wish to add two elements 3 bar plus 1 bar, so what we get, this is nothing but 4 bar. And if we wish to add 3 bar plus 4 bar, Okay, so what we get, 3 plus 4, this is 7 bar, but 7 bar is not here, so we divide it by 5 and get the remainder. Okay, similarly, so what this Zn is an abelian group with this operation plus. Okay, now let us talk about group of units. Okay, so what is group of units here? So suppose we are defining here multiplication. Okay, there are two elements, r bar and s bar. We define multiplication r dot s whole bar. So is this with this operation, this Zn is not a group. Okay, why it is not a group? Since there is 0. Okay, wait a minute. uh, we are taking Z star. Okay, Z star, yeah. We are removing 0 bar from here, and we are thinking about is it a group with this operation? Is it a group? Okay, so sometimes we see that this is a group, but sometimes it is not a group. Okay, so for example, if we take Z5 star. Okay, so oh, there is no 0 bar, so 1 bar, 2 bar, 3 bar, and 1. Okay, so this is obviously a group. You can check it with operation multiplication. This is a group, but this if we take another example, if we take Z6 star, then what is it? 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. And if we multiply 2 and 3, then what we get? This is 0 bar, and this is not an element of Z6 bar. Okay, Z6 star. So the closure property doesn't hold. Okay. Okay, so we think of some group of units. So UN, what is UN? UN, you can also write it as UZN. Okay, so this is nothing but those elements of Zn which have multiplicative inverse. Okay, so multiplicative inverse of r bar exists. Okay, that means what? That means there exists some. Okay, there exists some element s bar, say s bar. Okay, so there exists s bar inside JDM such that r bar to s bar equals, sorry, this is 1 bar. Okay, so one can easily calculate that what is this condition reduces to the following condition. This R bar is inside JDN, says that the GCD of R and N is 1. That means R and N are co-prime. Okay, so you know very well that uh, if you wish to calculate order of this UN, okay, order of UN, then this is nothing but phi n. Okay, phi n is what? This is Euler's phi function. Euler's phi function. Okay, so one can easily check that if we take two elements which are co-prime to n, then if we multiply then those two elements, then that will also be co-prime to n. Okay, so closure property holds in this un. Closure property holds, and similarly you can check all other things. So this is a group with operation multiplication. This is in fact an abelian group. Okay, this is an abelian group, but this is sometimes cyclic and sometimes non-cyclic. So there is some condition on n when it becomes cyclic. So I'm not going into detail that one. So this was the example of un. Okay, another example is what if we see, suppose S1. So this is circle group. Circle group is what? So it is collection of those complex numbers which are which have the modulus 1, absolute value 1. Okay, so this is you can write it also as e to the power something, e to the power I theta, where theta is a real number. Okay, so this is a circle group. This is a group with operation multiplication. Okay, this is also an abelian group. Okay, so this is also an abelian group. Similarly, we have some more groups like we can write cyclic group. Pn is what? Pn is those complex numbers which are okay. So here n is fixed, so z to the power n is 1. That means this is the nth roots of unity. Okay, this is also a group with respect to multiplication operation. Okay, and there is some more group which is p. Okay, so p is what? P uh, is collection of those complex numbers such that z to the power n equals 1 for some n. Okay, for some n. So it is nothing but union of all pn's. Okay, it is union of all PNs. So this is the PN is what? PN is isomorphic to Zn, that means it is cyclic, but this P is non-cyclic abelian group. Okay. One thing I wish to tell you that I am unable to see you all, and I am unable to see your expressions also. So please tell me if there is some problem. Okay. Okay. So now let us come to some more groups, like some up to here we were talking about some abelian groups. Okay. So now let us see some examples of non-abelian groups. Okay. So there is an example of non-abelian group. This is a quaternion group of order 8. Okay. So you know very well this is nothing but plus minus I plus minus j plus minus k. Okay. So I'm not going to detail of this one. So you know very well that this is also a group with respect to multiplication operation, in which multiplication is defined in such a way that I dot j equals k, uh, j dot k equals I, k dot I equals j, and k dot j is equal to minus I, and so on. Okay. So this is since you know I dot j is what? This is k, and j dot I is minus k. So this is non-abelian group. Okay. This is an example of non-abelian group. Now let us come to some non-trivial groups. According to me, these were trivial groups, but now we will talking about some non-trivial groups. So first of all, we will talk about some transformation group or symmetric group. Okay, symmetric group. So suppose we have some non-empty set X, and if we consider some collection of all bijective maps defined on X. Okay. So Cmax is what? Cmax is collection of bijective maps, okay, defined on X. So you know very well that uh, composition of two bijective maps is again bijective. Okay. So closure property holds in this group, obviously. That means if we have two elements here, okay, so that means composition of G composed with F is also a member of Cmax. Okay. So composition of maps is composition of two bijective maps is bijective. So that means the closure property holds in this set. And if we think and you know very well that this composition of maps is associative in general, so it holds here also. So composition of maps is associative. And if we think about identity map, defined on X. So you know very well that this identity map is a bijective map. Okay, this is a bijective map, and if we compose it with any other map, then what we get? We get the same map. So this is an identity element. Okay, so this is an identity element. Okay, so and similarly we can think about inverse of a map. Okay, so we know that if f is bijective, then its inverse exists. Okay, so inverse of f is what? F inverse, and f inverse, if we compose it with f, then what we get? We get identity map. So inverse of every element in CMX exists. So clearly this CMX is what? This CMX is a group. Okay, this is a group with respect to binary operation composition of maps. Okay, so this is in general a non-abelian group. Okay, and we will tell you why it is non-abelian group in general, but for some particular examples it is also a group, it is also abelian. Okay, so first of all, we think of suppose there are two sets. Okay, there are two sets x and y such that they have same number of elements. Okay, okay, there are two sets x and y in which number of elements are same. Then we see that the sim x and sim y both are isomorphic. Okay, why is it so? So what is isomorphic? You know very well, but I'm just telling here. So if there is a function f, suppose f is a function from two group, there is a group G1 and another group G2. So f is homomorphism. F is called group homomorphism if A O1 B is equals f of A O2 f of B, if it holds for every member A and B of G1. So we say that f is a group homomorphism. And if f is also bijective, then we say that f is an isomorphism. Okay, so f is an isomorphism. So f is a bijective homomorphism. Then we say that f is an isomorphism. Okay, group isomorphism. And if there is an isomorphism between G1 and G2, then we say that G1 and G2 are isomorphic. Okay, so these two groups G1 and G2 are isomorphic if and only if there exists and one and two group homomorphism between them. Okay, so these sim x and sim y, these both are isomorphic. Why both are isomorphic? Can you define group homomorphism from sim x to sim y? Obviously yes. How? Actually you have what? You have a number of elements of in x is same as number of elements in y, or you can say cardinality of x is same as cardinality of y. So if cardinality of x is same as cardinality of y, then you will be knowing that there exists a function. Suppose there exists a function phi from x to y, which is bijective. Okay, which is bijective. Okay, so if there is a bijective, fix a bijective function phi, and we have a function f in sim x, suppose f in sim x. Okay, so if we conjugate it by phi, then what we get? So phi composed with f, I think it is not correct. Wait a minute. Okay, yes. Phi inverse composed with f and composed with phi. So clearly this is a bijective map from where to where? From y to y. Okay, so this is a map, this is a bijective map from y to y, so this is an element of sim y. Okay, so for every f inside sim x, we have an element phi inverse composed with f composed with phi in sim y, and if we define a function from sim x to sim y by sending f to this element, so this will be a bisective group homomorphism. Okay, that means these two groups are isomorphic. Okay, so that means what I wanted to tell you, that only number of elements in x matters. Okay, so if number of elements in the set different, then the symmetric group defined on that one will be different. Okay, so suppose we are talking about finite groups. So if we take, okay, if we take number of elements in this set, okay, this sim x is what? This is called transformation group. Okay, transformation group or permutation group, whatever you can think of. This is transformation group or symmetric group or permutation group. Okay, transformation group. Okay, so if number of elements in x is n, then this sim x is denoted by, we denote it by Sn. Okay, and its elements are also denoted, if we take this x as the set 1 comma 2 comma 3 and so on n. Okay, so this is a simple way to write. So the elements of Sn will be what? the bijective maps from this set to this set. Okay, so okay, so I wish to tell you that why it is non-abelian. If we take number of elements in X is 2, so sim2 is what? That means S2. S2 is nothing but first one is identity map, and second one is we have two elements. Okay, so 1 and 2, and identity map was sending 1 to 1 and 2 to 2, so we are sending 1 to 2 and 2 to 1. Okay, in another notation we can also write it as 1 comma 2. This is a transposition or a cyclic notation. Okay, so there are only two groups, and you can clearly see that this is nothing but Z2. That means isomorphic to Z2. Okay, so this is cyclic group. Okay, but if you take number of element in AX is 3, then what is S3? S3 is nothing but identity map 1 2 1 3 2 3 1 2 3 and 1 3 2. Okay, so and what is this notation? This notation tells that 1 goes to 3 and 2 goes to 1 and 3 goes to 2. So we are writing in this form. So clearly you can see, if we multiply these two elements 1 2 and 1 3, what we get? So we will multiply it by this side. So 1 goes to 3. Okay, 1 goes to 3 and 3 goes to 3. Since 3 is not appearing here, so 3 is fixed by this map. So 1 goes to 3 and 3 goes to 3. So 1 is what? 1 is going to 3. So now 3 goes to 1 here, and 1 goes to 2 here. So overall 3 goes to 2 here, and 2 is fixed here. So 2 goes to 2 and 2 goes to 1. So 2 goes to 1. This cycle is completed. So we got that this element is 1 3 2, and if we multiply 1 3 by 1 2, then what we get? We get 1 2 3, and these two elements are different, not equal. So this element is this group S3 is non-abelian. Or you can say, similarly you can say Sn is non-abelian if and only if n is greater than 2. Okay, so this is our symmetric group. And you can also think uh, you can think of what? You can also think of the series of symmetric groups. Okay, since any symmetric group contains all the previous one. Okay, and in fact more copies of previous one, but in natural manner, it yeah, yes, if you wish to see, then that suppose you have 1, 2 and 3. Okay, so if you add 4 here, okay, so some maps are included. Okay, so similarly, if you will be seeing here that there are only two elements, okay, identity and 1 2, and here identity and 1 2, identity and 1 3, identity and 1 4. So there are more copies of S2 in S3. Okay, but in natural manner it is included here. So we can see that any symmetric group is uh, in includes, that means embedded in the next one. Okay, this was symmetric group, and I think you will be knowing all other things like what is even function, or what is even permutation, odd permutation, transposition, and other things. So I'm not going to detail. So just I wish to introduce some other group like what is alternating group. Okay, so alternating group. What is alternating group? So any element in Sn. So if you have an element F in Sn, so if it is even, if it is even, then we collect it. Okay, F is even permutation. Okay, and we collect it and we say that this is nothing but an. Okay, so you know very well that what is even permutation, since every permutation can be uh, written as product of cycles. Okay, and every cycle can be written as product of transpositions. Okay, so you can think of that any permutation can be written as product of transpositions. So, and number of transpositions may be different, like if you have an element 1 2 3. Okay, so you can write it as 1 3 and 1 2. Okay, you can also write it as 1 3 1 2 1 3 and 1 3. Okay, okay, so there there are two transpositions here, but there are four transpositions here. Okay, so uh, for any permutation the number of transposition may be different, but they will either be even or odd. It will be always fixed. So those permutation are called even permutation if they can be written as product of even number of transpositions. Okay, so collection of all even permutations is called alternating group. Okay, and it is closed. Why it is closed under composition of maps? Since if we take any two even permutations, then product of these as we know that sum of two even numbers is again even number. So similarly the product of two even permutations is again an even permutation. Okay, so this is closed under multiplication, and it is clearly you can see that inverse of any even permutation is again even. What is inverse of any element? You can see, if we wish to find inverse of this element, then this is nothing but, okay, and you can write it also as 1 3 2. Okay, so the number of transpositions, number of transposition are not being changed. So inverse of any even permutation is again even permutation. So this is a subgroup of Sn. That means it is also a group, and you know very well that it is this An, and I haven't told here that number of elements in Sn is what? Number of elements in Sn is nothing but n factorial. Why it is n factorial? You know that number of maps from a set to another is what? So wait a minute, I am going to tell that what is number of elements. So if we have two sets, x and y, having m and n elements, okay, so number of maps from x to y is what? This is nothing but n to the power m. Okay, this is number of maps. Okay, number of maps from x to y, it is n to the power m. Why it is n to the power m? Since if we have m elements here and n elements here, okay, so how many choices for one is? There are n choices, and similarly for every element in x there are n choices, so it will be n multiplied by n. How many times? M times, so it is n to the power m. Okay, and if we think about injective maps, so number of injective maps from x to y. So if we have less number of element in x than y, then we can define injective maps. But if there are more elements in x than y, so we cannot define injective map. So what will be injective map if m is less than n, or m is less than or equal to n? So it will be nothing but NPM. Why NPM? Since there are n choices for 1, and how many choices for 2? There will be n minus 1 choices. Similarly, for m, there will be n minus m plus 1 choices. Okay, so product of all these things will be npm. That means this is nothing but n factorial divided by n minus m factorial. Okay, so number of injective maps, and you know very well that if there are same number of elements in so then the injective maps, an injective map will automatically be surjective onto. Okay, so the number of 1 1 onto, that means bijective maps. What will be the number of bijective maps if there are same number of elements? and it will be same as NPN. Okay, so number of bijective maps, it will be NPN, and this is nothing but n factorial. Okay, so okay, so that means I wish to tell you that the order of this symmetric group is n factorial. Okay, so now suppose what will be the order of alternating group? So if we have an even permutation, and if you multiply it by any odd permutation, then what we get? We get odd permutation. Okay, so so um, from here we can conclude that number of even permutation is same as number of odd permutations in Sn. Okay, that means order of An is what? Order of An is nothing but, okay, order of An is what? This is n factorial by 2. Okay, so I am taking little bit more time. Okay, so I'm going to other example is alternating group, and you know very well that this is this one is normal subgroup, since index an in sorry, index of Sn in a index of an in Sn is 2. Okay, so you know that if there is a subgroup which have index 2, then it is automatically normal. Okay, and one more thing, that An is what? An is a simple group. An is a simple group if n is greater than 5. Okay, An is simple group if or you can also say that n is not equal to 4. Okay, n is not equal to 4. So what is simple group? You know very well that what is simple group? Simple group is a group in which there is no proper non-trivial non-trivial normal subgroup. Okay, so what is normal subgroup? Normal subgroup, a subgroup H of a group G, it is called is normal. It is normal if G inverse is H for every G. Okay, that means every conjugate of H is H itself. Okay, so then we say that this H is normal in G. Okay, and you know very well that in G, in any group G, the singleton identity and G are always normal. Okay, so these are called improper and trivial normal subgroups. So if a group don't have any normal subgroup other than these two, then it will be called a simple group. Okay, so this An is example of a simple group. Uh, Example of simple group. Okay, so this A4 is not simple. A4 is what? A4 is identity 1 2 3 1 3 2 1 2 4 1 4 2 1 3 4 1 4 3 and 1 3 4. Oh, okay, 1 minute. 1 2 1 2 3 1 2 4 1 3 4 1 2 4 and 1 4 2. Okay, and 1 2 3 4 1 3 2 4 and 1 4 2 3. So this is A4, and we have a subgroup V4. That means you can also say clients 4 group. This is identity 1 2 3 4 1 3 2 4 1 3 and 1 4 2 3. This is a subgroup of A4 which is normal. Okay, this is a normal subgroup of A4. That means A4 is what? A4 is not simple, but any other an n with n is not 4, then it will be simple. Okay, so clearly A1 is what? A1 is, what is A1? Oh, I'm not talking about A1 but A2. Okay, so A2 is what? A2 is A2 is what? This is singleton identity, and okay, just singleton identity. So this is trivially normal, trivially a simple group. Okay, since it doesn't have any other subgroup, so we can think of it. Okay, and A3 is what? A3 is identity 1 1 2 3 and 1 3 2. Okay, so this is isomorphic to Z3. This is okay, so this is a simple group. Okay, and A4 is not simple, and for n greater than 4 it will be simple. Okay, it can be proved. Okay, so this was alternating group, and now let us talk about some matrix groups. Okay, or one more thing, there is dihedral groups, so it will be very beneficial for you all. That what is dihedral group? Dihedral group. Okay, so uh, if we have n, n is some natural number. Okay, so for some extent we are taking n greater than or equal to 3, so that we can define we can form a regular n-gun. Okay, so if n is 3, then what is regular 3 gun? You know very well what is regular 3 gun. Regular 3 gun is equilateral triangle. Okay, my drawing is not so good, so please bear with us, and let us uh, give some names to these vertices. So 1 2 3, and we are talking about maps. Is there some problem? Am I audible?
No, sir. Please, sir, continue.
Okay, okay. So this is equilateral triangle, and the vertices of this equilateral triangle is labeled by 1 2 and 3. Okay, so if we are taking some those isometries, what are isometries? Just quickly tell about what is isometry. So in R3 we are talking about R3. What is isometry? So we know very well that R3 is a metric space, and distance function, you know. So F is an isometry. Okay, isometry. What is isometry? Isometry is nothing but, so F is isometry if it is it is it is distance between any two member. So distance between fx bar and fy bar, where x bar and y bar are members of R3. So it is distance between x bar and y bar. So isometry is nothing but distance preserving maps, and these distance preserving maps automatically become bisective. Okay, so these are this we can think of this is subset of or subgroup of some sim R3. Okay, so isometry of R3 is nothing but the collection of all distance preserving maps from R3 to R3. Okay, so this is automatically becomes a group with respect to the composition of maps. So now we can think of uh, group of symmetries. Okay, so what is group of symmetries? If we fix uh, any group of symmetries. Wait a minute. So group of symmetries in if we fix any plane figure or any surface in R3. So if we take those isometries which fixes that figure, that okay, so the collection of those isometries also form a group, and that is called group of isometries. So we are talking about a dihydral group, so we are taking plane figure. Okay, and plane figure, we that means we are talking about the subgroup of isometries in R2. Okay, so we have a regular three gun. Okay, and we are talking about those isometries which fixes this plane figure. Okay, so what are those? So first of all, okay, so if we take identity matrix, then it will fix this figure. And if we take a map or which rotates this figure by 120 degree, okay, and about this where center of gravity here, okay. So then that map we are denoting that one by R120, okay. This is the rotation by 120 degree, okay, about this O. Similarly, if we take rotation by uh, rotation by 240 degree, then we again see that this plane figure is fixed. And if we wish to take some, okay, this figure is not so good, okay. Okay, I'm assuming that this is passing through the same line, same point, okay. So this is a line, and this is perpendicular here and midpoint. So if we reflect the whole thing about this line, then what we get, this point 1 is fixed and 2 and 3 are interchanged. So reflection about the point 1, this is one, and similarly we can take reflection about the point 2 and reflection about the point 3, okay. So uh, if we multiply any two member here, so then we again see that we get any other member of this set. So this is called dihydral group, and we can denote it by D3, or sometimes we also denote it by D6, according to since there are 6 members, so we can also talk about D6 here, okay. So um, these are called rotations, okay. These are rotations, and these are called reflections, okay. And you can think that if we take any reflection, then inverse of any reflection is the same one, okay. So if we reflect it by this line twice, then we get the same thing, okay. That means we get identity map, okay. So so what we get, R1 square is identity. That means order of R1 or R2 or R3 is 2, okay. So these are um self inverses also, okay. So we can think these members as elements of symmetric group also, okay. So how can we see? So this is nothing but identity element, and this is what, this is R120, means we are rotating the whole figure by 120 degrees. So 1 goes to 2, 2 goes to 3, 3 goes to 1. So it can be written as 1 goes to 2, 2 goes to 3, 3 goes to 1. Similarly, what is rotation by 240 degree? So if we rotate it by 240 degree, then we see that 1 goes to 3, 3 goes to 2, 2 goes to 1. So 1, 3 and 2. Similarly, uh, if we take the reflection R1, then 1 is fixed and 2 and 3 are interchanged. So this is 2, 3, and R2 is what? 1, 3, and R3 is what? 1, 2. So this is nothing but S3 here. Okay. In this particular, this D6 is isomorphic to, this is isomorphic to S3. Okay. But if we think about other example like D8, dihedral group of order 8, then there are 8 members. Okay, 8 members, and what can we see? 1, 2, 3 and 4. So this is 1, 2, 3, 4. That means rotation by 90 degree, and rotation by 120 degree is what? 180 degree is what? This is 1, 3 and 2, 4. This is rotation by 180 degree, and rotation by 270 degree is what? This is 1 rotation by 1, 4 and 2, 3. Okay. And other reflections, you can think of reflections about these lines, these lines, and these 2 lines. Okay. So what you get? You get the reflection about one diagonal is what? Reflection about one diagonal is this is 1, 3. Okay. Reflection about another diagonal is 2, 4, and reflection about this line which is passing through midpoint of these 2 parallel lines. So what we get? This is 1, 4 and 2, 3. Similarly, reflection about this line is what? This is 1, 2 and 1, 2 and 3, 4. So this is what? This is D8, dihedral group of order 8, and we can see that this is a subgroup of symmetric group S4. Okay, so we can think any dihedral group as subgroup of S4, and this in general, what is dihedral group? D2n. This is D2n was this is also a subgroup of iso R2. Okay, which fixes the particular regular n gun. Okay, so group of symmetries of a regular n gun. Okay. Okay, so I'm not going to detail about this D2n, but just one thing I wish to tell, that it can also be written in the form of generators and relations, like its elements can be written as r to the power I, s to the power j, such that what is r here? R is rotation. Okay, so r to the power n is equal to identity 1. Okay, and s is what? S is reflection, so s square is equal to 1. And one more thing is that uh, um, s r s inverse is r inverse. Okay, correct. So this is presentation of this dihedral group. So what is presentation? And just quickly telling that what is, you know that what is a free group. Okay, what is free group? So suppose we have some set x. Okay, and we have some set x, and we take words defined on x, and we define some equivalence relation on those words that any two word are equivalent if they can be obtained by uh, introducing some more elements, wait a minute. If one element is obtained by other by introducing some such type members like x inverse or x inverse x. Okay, okay. So this will be equivalence relation on the set of all words, and if we take the quotient, then we can define this composition, means concatenation of words. This will form a group, and this is called free group. Okay, so I'm not going much detail. So this will be a free group, and we know that every group can be think that it is a quotient of some free group. Okay, so every group is a quotient of some free group. Okay, so there is some normal subgroup n of fx, and if there is some subset r of afx. Okay, and what is n? N is normal subgroup generated by R. Okay, so this G can also be think of x comma, or we can also write it as this x is called generators, set of generators, and this R is called set of relators. So this presentation, the way of writing a group is called presentation of group. Okay, so the presentation of dihedral group is what? The presentation of dihedral group, we can also write it as, this is not the way of presenting, but we can also write it as r comma s, such that this is generator, and what are relators? Relators are r to the power n s square, and we can write it as rs square. Okay, so this is presentation of dihedral group. Okay, So we don't have much time, I think. So just one thing I wish to tell, that what is matrix groups? Matrix groups. Okay. So as we know that a set of all matrices over any field like R, set of all EM cross N matrices, suppose EM cross N matrices. So set of all M cross N matrices. This is okay. So set of all M cross N matrices forms a group with respect to operation plus. And you know how plus is defined. Aij and Bij, these two are added, so we get Aij and plus Bij. Wait a minute. Bij. Okay, so this is an abelian group with this operation. But if we wish to define multiplication, then we think about set of all square matrices. Okay, so set of all square matrices with entries in R. So uh, is it a group with the operation multiplication of matrices? So you know very well that this is not a group with the operation multiplication. Why? Since you know that there are some members, there are some matrices which are not invertible. Okay, so now collect those matrices which are invertible. Okay, and you know very well that if a matrix is invertible, then its determinant will be what? Its determinant will be non-zero. Okay, so you can also write it as determinant of A is non-zero. Okay, so you can verify that this is a group with respect to multiplication of matrices, and this is called general linear group. Okay, and if we take some more subset, there is a subset of GLNR that is called what? Simple linear group, a special linear group. Okay, so it is we are taking those members of AM to R whose determinant is 1. So this is a special linear group. This is also a group with respect to multiplication, and uh, you know, I think if we think of center of a special linear group, then what is center of a special linear group? Do you know? Center of a special linear group is nothing but collection of those members of a special linear group uh, whose en whose entries are, that means they are diagonal matrices. Okay, so if we can write it as A is SLNR, member of SLNR, and A is diagonal. Okay, diagonal matrix. So This is center, and if we quotient it SLNR by its center of SLNR, okay, then you know very well that this is also a group, and this is a famous group called projective special linear group. This is very much important group, and there are some more groups like projective uh, projective general linear group and symplectic groups. So we don't have much time, so I don't want to go into details about these things. So may I stop here now, Ashish? Should I stop here?
Okay, sir. Sir, there are few questions.
Yeah,
Uh,
ask. I'm unable to hear you.
Hello, sir.
हाँ हाँ बोलिए.
Yes, sir, the question is there. One question is every
Mhm.
infinite group is isomorphic to a proper subgroup of its own. Is it true or false?
Every infinite group is
Every infinite group can have an isomorphic proper subgroup.
every infinite group can have an isomorphic proper subgroup.
Yes,
Okay. So if we think about suppose cyclic infinite cyclic group like Z, so it has a proper subgroup like 2Z or PZ, whatever, so which are isomorphic. Okay,
yes, sir.
it is clear. But if we take R or C, then I don't know whether it has an isomorphic proper subgroup or not. Okay.
Okay.
Okay, another question.
Yes, sir. One question here. Sir, one question is okay. Sir, the prime idea of simplicity of AL, alternating groups are simple groups. What is the main theme or proof idea?
I'm unable to understand the question. Please repeat.
So prime idea of simplicity of alternating groups
Mhm.
AL means
Prime idea. Mhm.
means how one should approach idea only main theme.
Okay. Actually, simplicity. I'm again unable to understand your question, but just I think you are asking about why AN is simple. Okay, is it okay?
Yes, sir. Yes, sir. Yes.
Okay, so simplicity means you know very well that it doesn't have any proper normal subgroup. Okay, so you can easily prove that if it has some proper normal subgroup, then we get a contradiction. Okay, so it is clearly this is a simple group, and why it is simple and SN is not simple, since you know very well that SN has a proper normal subgroup AN itself. So this is SN is not simple, that means, and AN doesn't have any other proper normal subgroup, so AN is simple for n not equal to 4. And there are some more simple groups simplest simple group is what? Simplest simple group is ZP. ZP is simplest simple group. Okay, and there are many other
Yes, sir.
simple groups which are like P, P. SLNFQ. Okay. Okay. So FQ, that means
Okay, sir. Okay.
FP. So this is also a simple group, and there are several simple groups. Okay. Okay. Another question.
Okay. Anyone has any questions? So please unmute yourself and ask question. We don't have any much question. Anyone? Okay. I think the question there is no question, sir.
Okay.
So okay. Thank you, sir. Sir. Okay, sir. Someone has again asked the same question.
Mm-hmm.
The proof of AN is simple group is very
Mm-hmm.
large. So
Mm-hmm. No,
just
no,
want to know. Yeah.
that is not so large. There is a question. There is a one proof given in the book by Professor Ramji Lal. You can see that is not so large. Okay, you can.
Okay, sir. So I think yes, sir.
Mhm.
Participants has got the answer. Okay.
Mhm.
Okay. Mr. Assis, please conclude the session. Assis. Thank you, sir. This is the initial talk.
Assis, you are muted.
Okay, sir, I think Assis has some problem, technical. So on the behalf of Assis, okay, thank you, sir, for giving your time and I believe that you are also available in future for our platforms and we will discuss some more properties of general linear groups, what are the normal subgroups of general linear groups and projective space group that you have discussed. So, okay, again, thank you, sir.
Thank you so much. But I wanted to discuss about some more things like these projective linear groups and general linear groups in some details. But there was lack of time, and I could not properly uh, express my this lecture due to being illness. Sorry for that, and I will be available next time. And
Thank you, sir. We will contact you
okay,
with suitable time and schedule. We again fix a date for more detailed lectures and
okay,
projective spaces also. Okay.
okay, okay.
Thank you, sir. Okay, now we are ending the meeting. Okay. Thank you, everyone, being here. Okay. Thank you.
Thank you, thank you.